So for graphing sine and cos, what we basically do is use points from our unit circle and plot them. And the axes family provides some really nice points. If you think about sine on your unit circle, sine is your y-coordinate. When the angle is 0, your y-coordinate is 0. Let's just draw a little unit circle off to the side here, right? I've got at 0, I've got the point 1 comma 0. And then I have 0 comma 1, negative 1 comma 0, 0 comma negative 1. Those are points on my unit circle. So when my angle is 0, my y value is 0. When my angle is 90 degrees or pi over 2, sine, my y value is 1. Then at pi, it's back to 0. At 3 pi over 2, or 270 degrees, it's at negative 1. And then at 2 pi, it's back to 0 again. And we can do the same thing and look at the x-coordinates and graph our cos graph. It too will go from negative 1 to 1 for its range. But a cos is your x-coordinate. At 0, it's at 1. At pi over 2, it's at 0. At pi, it's at negative 1. At 3 pi over 2, it's at 0. And 2 pi, it's back to positive 1. So here's a little program that I made with graphing sine and cos. I've got a little unit circle built in here. And right now, we're going to just start with, I'll unclick a couple of these other graphs. We'll just start by graphing sine. So we see the little blue dot there, sine. Now, on our unit circle, sine is your y-coordinate. So as I move this around, I've labeled from here to here sine. And that length is whatever value gets plotted as I drag it. So when we start back here, my y value is 0. And as I go up towards 90 degrees, so you can see the angle theta here increasing, you can see that that y value, the length of sine, gets close to 1. And at pi over 2, or 90 degrees, it's right at 1. Now, it's symmetrical as I go back on this side because my y value is decreasing. We get to pi, and your y value is 0 again. As soon as you go into quadrant 3, now my y values are negative because it's going down until it reaches the most it ever gets, which is minus 1 at the bottom, and then it continues back up to 0. So we can see in the graph, can you see in this sections here, this is quadrant 3 and 4, and sine is negative in quadrant 3 and 4. And quadrants 1 and 2, oh, wait for it, I want to clean, oh, there we go, fill that in. Quadrants 1 and 2, sine is positive. Now, on this unit circle, can you see cos is labeled as the red line? Because cos is your x-coordinate. It's whatever the length of your x value is. So if I add that graph as well, we start with an x value at 1. That x value decreases as you get close to 90 degrees, then increases. And so here in quadrants 4 and quadrant 1, you can see that your cos values are positive. But in quadrants 2 and 3, your x value would be negative, and so your cos value is negative as well. The graphs of sine and cos are exactly the same shape as each other, just one has been moved over like a translation of each other. If I take the red graph and moved it pi over 2 to the right, can you see that it would match up the blue graph perfectly? So when we get to adding our different translations together, there's some interesting things that can happen. What does that mean? If I translate it, this is just interesting math. What did I say? If I took my cos graph and I moved it 90 degrees to the right, we'll do it in degrees first. if I move my cos graph 90 degrees to the right, that would be minusing 90 degrees. Would that not shift it 90 degrees to the right? Or if I did it in radians, if we add something inside the function, that's going to move things horizontally. And if I had a minus pi over 2 or a minus 90, that would move it to the right. Now, if I did this, it's equal to the graph of sine of theta. So let's try this with a number, see if it actually works. Pick an angle. Pick an angle in quadrant 2. 130 degrees. Okay? 130 minus 90 is 40. Type that into your calculator. Then type in sine of 130. Are they the same? Because the graph says they shift over, they match up perfectly. Curiosity, is cos of 40 degrees equal to sine of 130 degrees? Oh, I'm like, my anticipation. Someone type it quick. They are fascinating. That is, like, it's amazing that we were able to do this without, like, I have no idea what your calculator, I have guessed, but I have no real idea of the decimal places that your calculator says when you put in cos of 40 degrees. And I have no idea even more with sine of 130. But I can say that those two are equal to each other because I recognized a pattern in the graphs. So we're going to graph sine and cos. We're also going to graph tan. Do you want to see what the graph of tan looks like? No, but I'll show it to you anyways. Good answer. Now, on your unit circle, tan is sine over cos, but if you actually wanted to figure out how you would graph it and what the value of tan is, if you actually draw a tangent line at that point P, and whatever length from point P to the positive x-axis or negative x-axis, that length is what the value of tan is. So you see this green line? That green line is the value of tan. Now what happens as I get farther and farther up here? Do you see how it fires off to infinity? And do you remember what happens at 90 degrees for tan on your unit circle? What was the value? Undefined. Because if I drew a tangent line at 90 degrees, can you see that it would be parallel to your x-axis? That green line would never touch your x-axis. And as soon as I go over into quadrant 2, now it's pointing in the negative direction. And so your tan values here start coming negative. Here, they go back positive, and it cast rule. And it kind of looks like a bunch of x cubed graphs all together. Now, eventually, not for a while, but just for fun, you'll be graphing cosecant, cotangent, and secant, so we can, woo, okay. There you go. Does that look like fun? You can think of them as toboggan runs. Woo! Oh, sorry. The sine guy's really having fun right here. Anyways, okay. So we'll add to our notes the graph of tan as well. And our graph of tan has asymptotes at the places where things are not permissible. Okay, so let us look at some properties of these. We can take out our highlighter. Okay, a function that repeats itself over regular intervals is called a periodic function. So in this example, if we look at one period of this graph, and they've labeled that from here to here, that yellow section, you could just copy and paste it and keep gluing it on the ends, and it repeats itself over and over and over again. The length of that amount of time that it takes to repeat itself is called the period of the function. So for our sine graph, it has a period of 2 pi. It takes one full time around the circle to get back to where it started from. So we could combine it back to our unit circle, and we can say that our period is 2 pi. A couple of other important things that we can get from this graph. We can say the domain of a sine graph is everything. It keeps on going forever, to the left, to the right. You can plug any angle in, because you can go around the circle as many times as you want. You can do sine of 3,630. Mental math, anybody want to say what the answer is? No? It's on your unit circle, right? If we knew that 3,630 was coterminal with 30 degrees, sine is your y-coordinate, you'd say that's equal to a half. Positive quadrant 1. And the values keep on going. The zeros, or the x-intercepts, and this is where we're going to write off to the side, there's a bunch of them. So if we started listing them, we would say there's an x-intercept here at 0. There's one at pi. Then there's one at 2 pi. Then there's one at 3 pi. Then there's one at 4 pi, dot, dot, dot. And if we started looking in the negative direction, we've got negative pi, negative 2 pi, negative 3 pi, and it continues. And mathematicians want to write them all down without having to write forever, because there's an infinite amount of them. So we have to look, what are ways that we could write this down quicker? And we look for a pattern. What do I notice for my numbers? I've got 0, 1, 2, 3, 4, 5, 6, 7, 8. My counting number is positive. I've also got my negative numbers. Negative 1, negative 2, negative 3, negative 4, negative 5. If I put those together, what are those numbers called? All your positive and all your negative numbers combined. But only whole numbers, not decimals. They're called our integers. So we could say that our zeros, does zeros have, oh, it doesn't have an E. Or does it? Our zeros are k times pi, where k is an integer. And there's our symbol for integer. And that way we can write them all without having to write them individually. Does that make sense? K times pi, where k can be any integer. That lists them all. Negative 5,380, it's included in there. That's an integer, without having to write that one down. When we look at our y values, we have a maximum value at 1 and a minimum value at negative 1, so we can say that the range is from negative 1 to 1. You can either write it in set notation like that, or in interval notation. We could look at the same thing for our cos graph. Do the same kind of highlighting. Cos is another periodic function, also with a period of 2 pi. I personally, when I'm figuring out a period, I like to start from a maximum and say, when am I back to that maximum again? Well, I went from 0 to 2 pi. My period is 2 pi. You can figure out the period from any point to any point. So they decided to start from a minimum here and see how long did it take to get back to the minimum again and measure that length. Either way, those lengths will equal 2 pi. The amount of time it takes to repeat itself, the one period, will be 2 pi. The domain of cos is the same as the domain of sine. The zeros of cos. So let's see if we can figure this out before looking ahead. We've got one here, pi over 2, then 3 pi over 2. The next one happens to be at 5 pi over 2, and then 7 pi over 2, and it keeps going. The negative ones start at negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, dot, dot, dot. So what do you notice? It's not quite as easy as sine, where it was just integers times pi. Okay? But there are some things that we could notice in here. What do you notice with the numbers? Double and one less. Okay. What are these numbers called? 3, 5, 7, 9, odd. They're odd numbers. So if I wrote this out in words, would you say that if it was odd number times pi over 2, does that kind of make sense? This is not mathematical. This is kind of English and math combined. We use a word. It's an odd number times pi over 2. Maybe even you want to put positive or negative odd number times pi over 2. So how do we write that mathematically? And that's sort of what Jesse was saying. He noticed a number pattern that if I take any number, I double it, add 1, or no, you said subtract 1. Okay? If I take any number and double it and subtract 1, I will always get an odd number. Does that make sense? If you took any number and doubled it, you'll always get an even number. So if I take any number, double it, and subtract 1, or add 1, I will get an odd number. So I could write the zeros to be 2k minus 1. That makes this odd times pi over 2, where k is an integer. Or another thing you could notice is that the distance between x-intercepts is always pi. So another way of writing the exact same thing would be to say, I'm going to start with one of them, which is pi over 2, and then I could add or subtract pi as many times as I wanted, where k is any integer. So when you're asked to write down the zeros of cos, you have to choose which of those two notations makes more sense to you. Do you like the odd number writing 2k minus 1 times pi over 2? Or does it make more sense to you to start with one that you have and say, every time I add pi, I end up at another x-intercept? Or every time I subtract pi, I end up at another x-intercept. So I could start with one of them and add or subtract pi as many times as I wanted to list them all. So you have to choose either this one or this form for writing all the zeros. I think your textbook kind of, no, they chose 2k plus 1. Adding 1 or subtracting 1 from an even number makes an odd number. And just like sine, we've got a maximum of 1, a minimum of negative 1, and the range is from negative 1 to 1. Okay? Some other things to highlight. Okay? Ooh, that's a little highlighter. Let's go bigger. The amplitude is the distance from the center line to a maximum or a minimum. So the amplitude of our function is this distance. We often, when we graph, will be putting a dotted line, not an asymptote, but a dotted line for your center line. And sometimes your center line is called an average. Sometimes it's called a center line. And sometimes, this is my favorite one, sometimes it's called the sinusoidal axis. So there's your word of the day, sinusoidal. Sounds like you've got maybe a little bit of a nasal infection, but no. Anything that has to do with sine or cosine graphs, sine and cosine graphs put together are called sinusoidals. So if your parents do ask you, what did you learn today? You can just say sinusoidals, and they probably won't ask you anything more about school the rest of the day. It's a good plan. So our center line, and we'll be labeling it as well, is a horizontal line. Horizontal lines are always labeled with y equals, so we'll have y equals 0. So we can take our regular graphs of sine, cos, and tan and apply all the transformations that we've learned from previous classes to them.